do this later on. Admit all these people. Right. So just to make sure that you're in the right place, this is EE5137 Stochastic Processes. I'm Vincent Tan, and I will be teaching this module. You can see all the details about grading and so on and so forth on this sheet of paper in Luminous. Okay, so all the stuff is in Luminous as usual with all the other classes. So I guess the Zoom people cannot see what I'm doing here, but it's okay. So in Luminous, you can see all the details here. All the reference books are here. We will be using Stochastic Processes Gallager, the last one. Okay. Then the homeworks are here. Okay. And then the past year quizzes and exams are here. So I've already uploaded 3 quiz ones. Then handwritten notes are here. The handwritten notes are just for my own reference. It's not really notes. Okay. I will also upload the handwritten notes that I really do in the lecture itself. But my handwritten notes are not as good as what I go through, what is present in the book. So you should always refer to the book. Okay. So previous years, people want my handwritten notes for some reason, but they should not be treated as the usual notes. Okay. All right. So let me go through this carefully. Okay. So my name is Vincent Tan here, and I will be teaching this module entirely. So unfortunately, you're stuck with me for 13 weeks. It's actually 11 weeks because we're on a Friday, but I'm not going to be lazy and only do 11 lectures. We are going to do 13. Okay. Last time I taught this was the pandemic, right? Then unfortunately, because a lot of changes, I had to do 12 instead of 13. So, but this time we're going to do 13, all 13. So for Chinese New Year and Good Friday, we are not going to be here. We cannot be here, but I'm going to record, so everyone will have to watch on Zoom like these people here. Okay. So my name is Vincent Tan. This is my office in the engineering department. This is my office in the maths department. But for the purposes of this module, I'll be here. Office hours I will announce, but most likely on Thursday afternoon, because I want to help people with the homework, which is always due on Friday. This is my email. This is the grader. In case you have any issues with the grading, you can ask her. She will be grading the homeworks. I will be grading all the quizzes and exams because those are more sensitive. Okay, the class time is, okay, you know the location if you want to show up is here. So this is a course on stochastic processes. The emphasis of this course is on mathematical rigor of principles and concepts in stochastic processes with an eye towards modeling real-world systems. Students are expected to do simple proofs in addition to rudimentary calculations, which means that this is not a calculation class per se, all right? 50% of the questions will be asking you to prove something. We will use the book by Gallager, Stochastic Processes, Theory for Applications. Specifically, we will go through probability, chapter 1 for 3 weeks, Poisson processes for 3 weeks, finite state Markov chains for about 3.5 weeks, and the rest for the remaining time, 3 to 4 weeks here. So this detection theory is in chapter 8. Estimation theory is in the book, is in chapter 10. But I find that the material there was not very good, so I wrote my own notes. But I'm still massaging them to make them really good before uploading. So all the information can be found on Luminous. Okay. Like it or not, I'm a big fan of homework, especially for math classes. But homework is meant for you to collaborate with one another, to work together, so I don't assign too much of a percentage to it. You are expected to get 10 marks. Okay. So the majority of the marks go into quizzes and exams. Okay, the first quiz is on week 4. So this class, this is the 4th time I'm teaching this class. I always put the first quiz on the 4th week unless there's another pandemic. Last time I taught this was very messy. Why I put it on week 4 is because I want people to know probability very well. As I said, the first 3 weeks are on probability. If you do not do well for the first quiz, means that you need to back up. Okay, so the first quiz, It's usually very difficult, I tell you first. And there are 3 examples there in Luminous, because I want to wake people up. But you won't get penalized too much because you only lose 12%. You still have a lot of percent to make up the marks. Okay. All right. So, okay. So I want to talk about homeworks. Very important. Most of the homeworks are taken from the book, so you need to have the book. The book is on Luminous. There will be approximately 11 homework assignments. The first one is already there. So what is the grading scheme like? Okay, no extensions at all will be allowed because I don't want to keep track of who is asking for an extension or not. Okay, you are strongly encouraged to collaborate with one another. So this is to help you work with each other and to gain an improved understanding of the material. You should treat the homework very seriously if you want to gain anything out of this module. Because of manpower, or rather woman power issues, since my grader is a woman, we will not grade everything. So my homeworks, there is a compulsory part and there is an optional part. You need to do all the compulsory questions, but a subset of the compulsory questions will be graded. Okay? You will receive the solutions to everything, the compulsory and the optional questions. Yeah, as I say here, there are many problems that are optional. You don't have to do this, but they are a good vehicle for learning. Solutions will be provided. So again, to simplify my life and my grader's life, how do we grade? We don't grade very finely. We don't give you 98.2 marks. Why? Because people will be asking me, why don't you give me 1.8 marks more to give me 100, right? We are grading in a very cost scale, 0, 1, 2, 3. So if you get 75% of the questions right, most of it right, you get 3. We quantize it to 3. So if you don't turn in, or you turn in 1 second late, you get 0. Okay? So if you anything in between, you get 1 or 2. All right? But people think that I'm very harsh because I don't allow any extension. That's not true, because I'm a very nice person. So here, 11 or 10 homeworks, right? Depending on my stamina at the end of the semester. There may be 10 homeworks only, all right? You are allowed to drop the worst 2, all right? So if there are n homeworks, we only take the average score or the total score of n minus 2 homeworks. So you're allowed to have 2 homeworks that are 0, 0. And you choose to get full credit for the homeworks. Understood? Yeah, so you don't have to ask me for extensions. You can, if you really need an extension, just drop it, just do the rest, and you're allowed to drop 2. So I will not entertain any requests for the homeworks. Very fair, right? Yeah, so this system, no one complains. So I'm a big fan of quizzes to make people be very hardworking, all right? So there will be 2 1-hour quizzes on these dates. The first quiz is on probability. The second quiz is on Poisson processes. Okay, the final exams, as usual, will be comprehensive, covering all the topics. Okay, all assessments. Actually, I don't really know about this yet. I don't really know how I'm going to do the quizzes, because do we do it here with all these people doing it at home, or everyone does it at home? I don't really know. Let me think about it and ask my colleagues. Okay. So I have a bunch of past year quizzes that you can use as practice questions, but some of the questions I will put into the homeworks. Okay. So this is a rough schedule here. Oh, by the way, I want to talk about prerequisites. What are prerequisites? Prerequisites are what you need to know before you actually do this class. Basically, you need a good undergraduate probability course. So in my Luminous, right? Oh, those people at home cannot see this. But here, books. This is the prerequisite book by Berzekas and Sisiklis. You don't need to know everything there, but you should need to know the first few chapters on probability. Okay, so this is what I expect people to sort of know. Okay, this Ross book is another stochastic processes book that is taught in many other schools, but I use the stochastic process Gallager book because that is from the school I came from. Okay, so you see all this? This is the tentative schedule. All right. So there are no surprises. When is homework 1 out? Where is homework 2 out? When is homework X due? When are the quizzes? They're all here. They're all in lecture, okay? All the quizzes are in lecture. And then the exam is, I think, on this date because the university says it's on this date. These are the references for what we're going through. This is completely optional. This one is, you need to read it. When I say read section X to Y, I really mean it. Those are the notes. So these are the logistical issues, logistical points I want to mention. Any questions? Any questions to the people at home? You can also say something, or unmute yourself or type. Any questions? You need to know probability. This is serious, okay? Even though we will go through probability for the first 3 lectures. Yeah, you need to know that. You need to know what's a random variable. You need to know expectation. You need to know variance. You need to know some form of laws of large numbers. Okay. Is this clear? Usually what will happen is that at around 7:20, right, we will take a 10-15-minute toilet break. No questions? Well, my experience with this sort of Zoom teaching is that these people here usually have a lot of questions, but we'll see. Okay, so how do I go back? Oh, here. Really no questions? Okay, so this class is on stochastic processes. We will learn about random variables, and stochastic process is really about many random variables. Okay, infinitely many random variables. Okay, so how do we deal with infinitely many random variables? So these are just some things, okay, that I've already said. I don't know why I wrote this down. So this is the main textbook. Okay, so if there are no issues, I will go ahead to talk. Everyone can see this properly, right? Those people at home can also see this, okay? So today's, I cannot bend down like that. I will sit down like that, okay? Today's lecture is on the reading is section 1.1 to 1.4.1 of Gallager's book. Okay. Sorry, this is the first time I'm here. I need to position myself properly. Otherwise, it's very uncomfortable. It's too high up. Okay, so this is the reading. So you're meant to read this part of the book. I cannot. Those people at home cannot see me. All right. So this part of the book is really on basic probability. What is a random variable? And how do we calculate simple things? All right, but different from an undergraduate probability class, here we are going to take a more formal approach, and we'll touch a little bit on measure-theoretic probability. Prof, are you going to share the lecture notes? As I said, right? As I said, Vivek, the lecture notes equals the book. So when I say section this of Gallager's book, these are the lecture notes. Vivek, is that understood? Is that understood? Yes, these are the notes. The book is in the luminous under books.
Yes, sir.
Okay, good. All right. So where do we start with? Where do we start from? We start with sets. Omega is known as the sample space. Okay. This is the set of all sample points or possible outcomes of a given experiment. Of an experiment. Space. Of an experiment. By the way, Vivek, I will also upload what I'm writing now, but it's the same as what I already uploaded. Okay. So for example, let us give some examples. Okay, this is very abstract. We don't like abstract things. Coin tossing is a standard model for probability. So in the coin tossing, what is a sample space? Well, you have two outcomes, heads or tails. All right. The dice throw, a throw of a dice. Omega is equal to 1, 2, 3, 4, 5, 6. So in these two settings, in these two contexts, all right, in these two sort of experiments, the sample space is finite. Finite sample space, because, well, these sets here are finite, right? Now, you can imagine many other scenarios, okay, where we have infinite sample spaces. Okay, so for example, omega can be the set of natural numbers. Okay, so suppose we go into a casino and we play the slot machine, okay, and every time it gives us $1 or $0, and we play for an infinite amount of time. Okay, so the sample space is actually the set of natural numbers n here. Okay, the sample space could be omega equals to 0, 1. Okay, you generate a random number from MATLAB, in MATLAB using RAND. This is the sample space. Okay, of course, if you generate a random number in MATLAB, it is inevitably quantized, all right, to some number of decimal points, but you can imagine that you have also have infinite sample spaces, which are going to be much more difficult to deal with mathematically. Okay. Now I want to introduce another important concept known as events. Okay. So events are subsets, or rather, okay, let me say legitimate subsets of the sample space, omega. Okay, so for example, for dice throw, let's define the event E. Okay, E is 1, oh, sorry, I meant to say even, right? 2, 4, 6. So that is a subset of omega, and it stands for the even outcomes of a dice throw. If there's someone asking me a question here, please let me know. Okay, so E is an event. It's a legitimate event because it is a subset. All right, so you can also define the odd. All right, these are odd outcomes. These are odd outcomes. This is a legitimate event. Events are subset of the sample space. Then you may wonder, sorry? What is the meaning of legitimate? So are there any illegitimate subsets? Yeah. It turns out that for finite sample spaces, like these very beautiful finite sample spaces, you can take the set of all subsets to be your events. Okay? But for these sort of more complicated infinite sample spaces, there are many intricacies that we will not have time to talk about. This belongs to a math class. Okay? But what we will need to talk about are some properties of events that make them be legitimate. All right, so let me make this precise. Okay, but before that, I want to remind you of some basic set theoretic notation. If we have events or subsets of omega, let's say A1, A2, AN, all these are subsets of omega. By the way, I use this as subset. This is subset equal in LaTeX. But sometimes I'm lazy and I use this, which is subset only in LaTeX like this. All right, these all mean the same thing. Okay, so even if I use this, okay, A is still a subset of A. Okay, so it doesn't have to be a strict subset. All right, if we have events, all these events, their union is denoted as A1 union A2 union ... union AN. So that's the union. Union is the set in which you have all the elements in any of the AIs, okay? Okay, sometimes we also write this as union up to n, I equals to 1 AI. Okay, if we are lazy. So the picture is as follows. If you have A1, A2, A3 here, okay, then the union is basically, just to remind you, color everything. Okay, the intersection is basically where they intersect. So that's the union. One good thing about teaching like that is I don't have to worry about my markers going out of ink like those, right? So this colored region is A1 union A2 union A3. Okay, so the intersection is denoted as the following: AI, or A1 intersect A2 intersect up to AN. Okay, is the set of points in omega that are contained in all the AIs. Okay, so the union is denoted as this, and written as this. It consists of all points in at least one of the AIs. Okay, sorry, this is not very beautiful. Okay, so the intersection is obviously here. Okay, there's an intersection. A1 intersect A2 intersect A3. Okay, hopefully everyone has seen this sort of simple things before. Okay, but this is just to set the notation so that everyone is on the same page. Okay, and the terminology intersection. Complement is also another interest. It's also another thing that we will have to deal with. Complement of A is denoted as A complement like this. Okay, but I don't really like A complement. Because why don't I like this notation? If you're a proper mathematician, you wouldn't like this. Because you do not know what you are complementing against. Where does A live in? Does A live in B, or does A live in omega? So to make things clear, we will have to do this. So that omega set diff A is a set of all points that are in omega but not in A. All right, so that is a complement of A. Usually we say complement of A if we want to be really pedantic, complement of A in omega. All right, this is better. Okay, yeah, okay, we don't have to say this. So sometimes, any questions? Oh, okay. So sometimes we also have to deal with funny sets, all right? So let's say we have to define the notion of a countable set. Sometimes we have to deal with it, not too often. If you don't fully understand this, it's okay. If you see this for the first time, a countable set is one in which the objects or the elements of the set, in which the objects or elements of the set can be placed in one-to-one correspondence with the natural numbers. Okay, so these are natural numbers. What does it mean to be placed in one-to-one correspondence? All right, one-to-one correspondence. Oh, sorry, wrong pen. One-to-one correspondence. All right. So how do we tell that the number of students here is equal to the number of students here in the Zoom? How? One way is, I go and count the number of students here, and I go and count the number of students here, the Zoom people. And if the numbers are equal, good, they are equal. Good, right? That's one way. What's another way? I will pair you with one student here. I'll pair you with one student here. I'll pair you with one student here. If there are no leftover people, then we also know that the number of people here is equal to the number of people at home. Okay, number of people at home I can see is 25, including myself at home, and this person is also at home. All right, but okay, modulo this issue, we can pair each person here with each person in the Zoom. So that means a one-to-one correspondence. Okay, let me give you some examples. Okay, so probably you know that, all right, example, oh, sorry, wrong pen. E.g., set of even numbers is countable. Countable. So a set of even numbers, let's call it E, is 0, 2, 4. Set of even positive or non-negative. Otherwise, I have to do more work. It's countable. Why? Why is it countable? Well, can it be placed in one-to-one correspondence with the natural numbers? Okay, look at this. I will associate 1 to 0, associate 2 to 4, associate 3 to, associate 2 to 2, associate 3 to 4, and you can see a natural formula that places these two sets in one-to-one correspondence with each other. But notice that the set of even numbers is very much intuitively. It's very much smaller than the set of natural numbers because there are many holes, right? Like in even numbers, in the set of even numbers, the number 1 is not there. The number 3 is not there. But even so, these two sets have the same size because they can be placed in one-to-one correspondence with each other. This is the strange thing about infinite sets. But these people here at home, they're only finitely many, only 25 people. And here maybe 25 people. So for finite sets to have the same size, they must have the same size. They must be one-to-one correspondence with each other. But for infinite sets, you see that they can be different size, right? Okay. So another example is the following. The set of all integers, z. So the set of integers z goes from like that, -2, -1, 0. So they can be positive and negative. So again, how do we place things in one-to-one correspondence with each other? All right. So let me make this a little bit longer. This is not so terribly important, but it's just for fun. You can place 1 in correspondence with 0. You can place 2 in correspondence with 1. 3 in correspondence with -1. 4 in correspondence with 2. So there's a very natural formula here that we can write down. Right? Okay, so the set of all integers z is also the same size as the set of all natural numbers. What is perhaps not so easy to see is the set of all rational numbers. Q is m over n, say, or non-negative. Okay, m bigger than 0, m is an integer. Okay, this non-negative. M is I'm sorry. M, n are integers, and m over n non-negative. This is also countable. Okay, so exercise. This is not so easy. All right, but here, I mean, you can do the following, right? So you can list 1, 2, 3, 4. This is the m part, and this is the n part. 1, 2, 3, 4, and so on and so forth. So every element of this infinite matrix here, so this is an infinite matrix. Every element of this infinite matrix is it corresponds to a rational number. You take m over n. Okay, it's a rational number. Then what we do here is how do we associate every element of this rational number to the integers or to the rather these natural numbers? Well, we go in this way. What color do you like? This color, I guess. This way, a systematic way, and so on and so forth. All right. So in a finite number of steps, I can reach any rational number. Okay. So that's the general idea. Of course, to write down the formula is a little bit troublesome. Okay. But this is the idea of countability, and we will sometimes need to use it. Okay. So, all right. So just now there was a gentleman in the front row here who said, well, he's a bit troubled by the legitimacy of these events. So we need to somehow define what is a good event, what constitutes as an event, even if it is a subset of the sample space. There are some subsets of the sample space that do not qualify as events. So we need to make clear what is a good event, what is a good subset that we can say that is an event. Okay, so again, we start off with omega being a sample space, being the sample space. Okay, so we have to define a very important notion known as a sigma algebra now. The class definition. The class of all subsets of omega that constitute or that make up the set of legitimate events, the set of events which are legitimate subsets is called a sigma algebra. Okay, and a sigma algebra, which is a set of subsets of omega, and a sigma algebra, let's say AI, where AI subset of omega satisfies three important properties. Number one, omega is an event. Does it make sense for omega to be an event? Omega is a subset of omega. All right, because I said that subsets can be the full set. So the first thing for you to be an event is that you need to be a subset of the sample space. And omega certainly is a subset of the sample space. So, okay, so the full set is an event for a set of subsets AI to be a sigma algebra. Okay. Now, then the other elements of the subset of the other elements, basically the other subsets AI need to satisfy some other properties. Okay. For all sequences A1, A2 that are events, their union is also an event. So informally, this is called closed under infinite union. A sigma algebra is closed under infinite union. So if I take some infinite, so what I have here is a sigma algebra, which is basically a subset. A sigma algebra is a set of subsets, these AIs, right? I start with this. Omega must be part of this family. And now I take any infinite sequence, I take any sequence of events inside this AI, I take any infinite sequence here, and I look at their union. If their union is not in this family itself, then we are not closed under infinite union. Then this whole thing cannot be called a sigma algebra. And it is not a good candidate to talk about probabilities. Okay, so close under infinite union. And part 3, for all A's that are events, i.e. A belongs to this family, this A here belongs to this family here, A complement equals to omega diff A is an event. This property is called close under complementation. These are not in my notes, but I'm coming up with them on the fly. Okay, so any sigma algebra must satisfy these 3 properties. Okay, otherwise it's not called a sigma algebra. And we can only do probabilities on sigma algebras. Okay, so In conclusion, the class of all subsets that satisfy 1, 2, 3 is called a sigma algebra. Sometimes you will see in some books, it's called sigma field, all right? Sigma field and sigma algebra mean the same thing. Okay, now here we only talk about 3 properties, right? But from these 3 properties, I can already ask you to do a lot of homework. Okay, but in order to spare you the pain of doing homework, now I will do some homework for you. Okay, so we are going to prove some things. Okay, fact, we are going to prove this. Phi, the empty set, is an event. This is the first non-trivial thing. Maybe this is kind of trivial actually, but why do we need to prove this? Well, we need to prove this because no one said that phi is an event here in our axioms. No one said that phi is an event. So what do we need to do? We need to combine our knowledge based on these above axioms in order to prove that phi is an event, empty set. Oh, by the way, the phi is basically omega complement. Okay? Right. So I already gave you the answer. But let's prove. Our first proof of this course. What a momentous occasion. Why? So phi equals to omega complement. Omega is an event. Any complements of events are events. Omega is an event by 1. Complements of events are events by 3. Hence, phi is an event. This is a proper proof. Is that clear? Well, people at home, is that clear? Very clear, right? Today, we will do many of these apparently simple things, but there will be one slightly non-simple thing. Okay, any questions? Fact. A1, A2, AN is a finite collection of events. Okay, this is the background, okay? Background statement. The fact is, so if A1 is a finite collection of events, then, okay, sorry, I'm being very illogical here. Here's the fact that we are going to prove. If A1 to AN is a finite collection of events, comma, then their finite union is an event. Didn't we have something similar to this just now? Didn't we have this? Can we just use this? Here we have an infinite, closed under infinite union. Okay? In what I'm going to prove to you, the claim here, the fact here, we have a finite collection of events. And we want to prove that the finite union is an event. Right? Is there any work to do? There is some work to do. If you say, oh, I give you this quiz problem, Professor, this is obvious, you get 0. Okay, because you do not know what you do not know, which is the worst. All right. So, proof. Use property 2, or rather, let's call it axiom 2. Okay, and let an plus 1 equals to an plus 2 equals to ... equals to empty set. Why can we do this? Because the previous fact, we already proved that phi, the empty set, is an event. All right. So this collection here, the sequence A1, A2, A3, all the way up to AN plus 1, AN plus 2, is a sequence of legitimate events. Is sequence of events. Furthermore, by 2, infinite union AI is an event. Right? By 2, not by any other thing, because now we only know 3, we know 4 axioms. We know 3 axioms plus 1 fact. Right? By 2, this is an event, but the infinite union equals to the finite union, because everything else is empty set. And hence, this is an event. Clear? So there's no jumping around. It's all logical. You know, what's the point of teaching this class? The point of teaching this class is not to teach you about stochastic processes. It's to teach you that there is an important lesson in life that is to think logically. You may forget about Markov chains that I'm going to teach you. You may forget about Poisson processes, but you must remember that there is a point in thinking logically that you will still remember when you are 60, 70, 80 years old, that you sat in this class and I said you have to think logically. All right, you may forget how to prove these things, but you need to know that there is something to prove. Okay, what's the next fact? After I talk about all these philosophical things, okay. Okay, the fact is that every finite, next thing we want to prove is that every finite or countable intersection of events is also an event. Okay, is there anything to prove? Yes, there is something. Why is there something to prove? Because the axioms only said union, right? The axioms only talk about union. The axioms didn't talk about intersection, right? Every finite or countable intersection is an event. Okay, so there's something to do because we have not talked about intersection yet. Is intersections, sigma algebras close under finite / countable intersections? We do not know until we proved, right? So let's consider the following. Okay, I'm going to write this like this. This I can run from 1 to n or 1 to infinity, doesn't matter. It takes care of both finite and countable. I'm going to be a little bit lax here. Okay, let's consider its complementation or complement. So there is a rule that says the following. Okay, this is called, what is this called? De Morgan's formula. Okay, so that is if and, so we have this relationship, and I think I need to make more space. So this is if and only if union I, AI, complement. Let's consider this. This is equal to intersection AI. Just by replacing the A's above with, just by replacing the AI complements above with AI, right? So this is called De Morgan's rule. And here we replace AI by AI complement. You can replace them by BI, it's fine. Maybe it's easier to say BI. Okay, let's just say BI so that people don't get confused. We want to show, what is our aim? We want to show that this object here is an event because it's an intersection. We want to show that this thing I circle is an event. Okay? If I'm given that the BIs themselves are events. So if we know that the BIs are events, then the question reduces to, is the intersection finite or countable? An event. Okay, so the proof goes as follows. We know that the BIs are events. We said so, right? So what about this guy here? Okay, let me use red color. What about this guy here, the complement? Is it an event? Each BI complement, is it an event? Why? Because we proved it in my first fact or second fact or something like that. Oh, no. No, this is part 3. Part 3 of the axioms, right? Part 3 already said that the BI complements are events. Now, unions, part 2, I guess. I cannot remember which part. Unions, part 2 says you are an event. And this infinite union, countable infinite union, is an event. We proved in one of the facts that finite union is also event. Where? Finite union. Finite collection, finite union is also an event. So regardless of whether we are infinite union or finite union, we are an event. So this is an event. Right? By one of the axioms for the infinite case or for the infinitely countable infinite case, or one of the facts for the finite case. All right? And then this is an event by closedness under complementation. Complements of events are events. And so this left-hand side is an event. So the right-hand side here is an event. That's the proof. Okay? So sigma algebras are also closed under intersection. This, I see some people who have a lot of confused spaces, so I'll repeat slowly. Okay? Okay, why? So let me say that, okay, we're going to prove that every finite or countable intersection of events is also an event. How do we start? Okay, we start by fixing BIs that are events. Okay, so these BIs are events, so let me be a bit more careful. This BI, I runs from 1 to n or infinity, let's say infinity. Okay, we fix these events first. All right, we want to prove that the infinite intersection is an event. That's what we're going to prove. I do not know which proof is a special case. No one told me. All right, but okay. I don't think it's a special case. Right, but then let's not be distracted by this. Okay, then the intersection here is an event. Okay, why so? Because we proved that complementation is an event. If BI is an event, BI complement is an event. This is by part 3, axiom 3. Okay. Union, infinite, countably infinite union or finite union is an event. So this is also an event. All right. But complementation, again, it preserves the fact that it is an event. So the left-hand side is an event. So the right-hand side is also an event. And we are done. Okay, so we go systematically. Can you see? Any questions? For axiom 2, countably infinite. But we proved in one of the facts here that if I have a finite collection of events, the finite union is also an event. No, that's the whole point of probability. We cannot deal with uncountable. Many things will go wrong. All right, that's why we need to restrict ourselves to countable union, countable intersection. You know what is the meaning of sigma algebra? What is the sigma there? Sigma in the past meant sums. By the Greeks, sums. And sums you can only sum over countable. You cannot sum over uncountable. That would be an integral already. So the sigma in sigma algebra really means countable union, countable intersection, because the sigma stands for sum. All right, good questions. Okay. All right, so coming to this student's question, let's write a remark. Okay, the remark is my last fact here. Okay, that does not have to be proof, it's just a remark. The class of all subsets of omega for omega uncountable, okay, e.g. omega is the closed interval 0, 1. the set of all subsets of this set, the closed interval, does not allow for probability axioms that we are going to talk about next to be satisfied in a sensible way. But this is not needed for our module. This sort of subtlety is not needed. This sort of subtlety belongs to a real analysis class. Real analysis means measure and integration class. If you have time, I believe everyone's very busy, but you can read about Vitali sets in Wikipedia. Okay, but I will not talk more about this. So the point here is that if we start off with sample spaces that are infinite and uncountable, all right, like this set here, the closed interval, open interval, whatever interval, and you want your sigma algebra to be very rich, in the sense that you want all subsets to be part of your sigma algebra, then you will run into problems when you talk about probabilities and measure. Okay, so but this does not belong to this class. I want to teach this, but they don't assign this to me. Anyway, so let's now talk about axioms of probability. Okay, so we again start off with omega sample space. Okay, and after we fix the sample space, we can talk about E, sigma algebra defined on the sample space omega. Okay, so E is a sigma algebra. That means E satisfies the axioms, the three axioms of sigma algebra. The three axioms include omega is in the sigma algebra, closed under infinite or countably infinite union, closed under complementation. These are the three rules of sigma algebra. Okay, omega and E are now defined. All right, a probability rule. Now we define the notion of a probability rule definition. A probability rule PR. Okay, maybe I don't use this notation. PR is a function that brings us from sigma algebra, brings us from subsets of the sample space that are legitimate events to the interval 0, 1. Okay, but a probability rule cannot be anything. It cannot be any function. It cannot be a very funny function. The first rule is that probability of omega must be equal to 1. The second rule is that whenever we write down something, we have to ask ourselves a question. Can we write down this expression? Can we write down this thing here? Probability of omega. Are we allowed to do it? And why are we allowed to do it? Who says we can do it? Do we know what is the subtlety here? The subtlety here is that the question is omega belonging to E? Yes, by axiom 1 for sigma algebras. Then it is legitimate to stick the omega inside here. If you don't have omega in E, you cannot even talk about probability of omega. You see the point? So it's very important. Now, for all A in E, probability of A is bigger than or equal to 0. Okay, cannot be negative. But this is already encapsulated here because the range, the codomain here is the interval 0, 1. 3. For all A1, A2 in E that are disjoint, I cannot spell disjoint. What is the meaning of disjoint? That means AI intersect AJ is nothing if I not equal to J. All right. Then we have probability union up to this, n equals to 1. So the probability of the infinite union. Why can we talk about the probability of the infinite union? Because of some axiom. I cannot remember which, but it's axiom 2, okay? Axiom 3 is complementation, right? So we can talk about this because we said that this sequence here, every element of this sequence is an event. So we are allowed to talk about this. This is an event. And so we can plug it into the probability operator. Otherwise, we cannot. Okay, so the claim here, the axiom is that this is the sum up to n equals to 1, probability of an. Now, if you, okay, if we probably have seen what is the meaning of infinite sum before, but formally, it is defined as the limit as m going to infinity, sum up to m, n equals to 1, probability an. Now, something is not very good here, although it's correct. I need to say one more word before I can use something here. I will never ever allow a student to write limit, because this is a sequence. This object here, inside here, is a sequence in M. Not every sequence has a limit. You can have jumping around sequences. So you cannot write limit unless you show that the limit exists. Right? Like the sequence -1 raised to the M does not have a limit. But this is okay. Why? Because this sequence here, let's call it Cm, is non-decreasing. It is only I cannot say it's increasing, it's non-decreasing because the probability values are non-negative. And if you have a non-decreasing sequence Cm, then it either has a limit or the limit is plus infinity. So it is legitimate to use limit here. Okay? So we have to be a little bit pedantic. This class is about being a little bit careful, right? So we cannot anyhow say things. First and foremost, this object here is an event. And the claim here is that if these guys inside here, these A's are disjoint means this, then this probability is equal to this. And it is okay to write limit here because this sequence or this series is only going upwards. Can only go upwards, cannot go downwards. Just now that strange sequence that I wrote down can go up and down, up and down. That's why there is no limit. Okay? So, okay, very good. So now we have the 3 axioms of probability. And what am I going to do? I'm going to prove to you about 8 facts. 8 facts. Some of them are very trivial, you may think, but all these are examinable. Okay? Fact 1, we are very logical people. The probability of phi is equal to 0. No one said that it's equal to anything, but intuitively the probability of the empty set is equal to 0. This actually is very tricky, very tricky. We need to make use of a bit of tools. Okay. You may think, oh, what is your first thought? Oh, look at the first thing I wrote here. The first thing I wrote here is, oh, take 1 minus something. 1 minus 1 is 0. Who said? Right? You can try to create a proof here, but something will be missing. So let me show you, okay, the proof for this. Apparently simple fact. So let an be equal to the empty set for all n in n. Okay, so we create a sequence of empty sets. The an's are disjoint. Because an intersect am is equal to empty set intersect empty set, which is empty set for all n not equal to m. That's the meaning of disjoint, right? Furthermore, the infinite union of the ANs is equal to phi, empty set. The union of empty sets is the empty set, right? Now let's consider probability of the empty set. But the probability of empty set, by using this relation here, all right, what we get here is that this is equal to the union an n equals to 1. This is what? Oh, now all the ANs are disjoint. So we are going to use part 3 of the probability rule. This part 3. Can you see this? Part 3. All right. So this is the sum. Oh, let me write this carefully. Let me write this as limit m going to infinity, sum up to m, probability an, n equals to 1. But what is this? M running to infinity, sum m, n equals to 1, probability of empty set. Right? Because all the ANs are empty set. But now we have limit m going to infinity of, now all these guys here, all these people here are the same. They don't depend on the index n. Hello? Hello? Battery problem. So all the probability phi, they don't depend on the index n. So this is equivalent to m times, sorry, wrong color, m times probability phi, right? Because the things inside don't depend on n. So we are just like, you go to the market and you buy an orange, you buy m oranges, each orange is $2. M oranges is $2m, right? Here, same logic. Because all the oranges have the same price, right? So here, we come to here. So we conclude that probability of phi is equal to limit m tends to infinity of m probability of phi. Right? So there are two cases here. Case A, probability of phi bigger than 0. Case B, probability of phi is equal to 0. There are only two cases in life, right? Because probabilities must be non-negative. And this is using part 2. We are not being very fast. We are using part 2. Probability of anything is non-negative. So there are only two cases. But this case is impossible, right? Because if it is positive, then the right-hand side here would tend to infinity. The left-hand side is finite, at most 1. This is a contradiction. And so this is the only choice left. So that's the proof. You see, it involves a lot of things, right? So to conclude, since probability of phi is a non-negative number, it must be that probability of phi is equal to 0. Okay. So this is a bit non-trivial. How about showing that probability of phi is equal to probability of A union phi? How did this person type the union? Equals to probability of phi plus probability of A. So probability of phi is equal to probability of A minus probability of A equals to 0. As any set A and phi are disjoint. I guess it's fine. Yeah, no problem. At least I don't see there's a problem round. Yeah, good. Another method. Oh, this is the alternative method. Very good. Okay, so I said we are going to prove 8 things, right? Unfortunately, this lecture is going to be a little bit dry. But sometimes it's exciting like this. You have alternative solution. But this lecture may be a little bit dry to some people, but nevertheless, we have to go through all this pain. All right. So if A1 to AM are disjoint, and we know what is this, the meaning of disjoint, then the probability of their finite union is equal to probability of AN. Okay. So the proof here, I'm not going to belabor the point. Apply axiom of probability 3. Axiom 3 is this one here, where we have an infinite sequence of disjoint events. We use the same trick. Okay, if we have only considered M, we set all the rest to be empty set. To the sequence, apply axiom 3 to the sequence A1, A2, all the way to AM, and AM plus 1, AM plus 2 equals to, all this equal to empty set. And we are done. Okay, so that is possible. So basically, once we have the countable union equals to the, once you have that the probability of a countable union is equal to the infinite sum, we also know the same for the finite union. Okay. And just to belabor the point, this is because the infinite sum, infinite union of AN in this particular setting is equal to up to M. Okay. Because the rest are empty set. Now the fact 3 to be proved is probability of A complement is equal to 1 minus probability of A. For all A that are legitimate events. Okay. So to do this properly, we note the following. Okay. The proof goes as follows. Omega is equal to A complement. Okay, so no one has any other special solution yet. Okay, so this notation you may or may not want to use. You don't need to know. But my professor last time used this to denote disjoint union. Okay, but doesn't matter. But the fact here is that omega can be split up into two parts, A and A complement. This is omega, this is A complement. Okay, so A and A complement are disjoint. So what do we know about disjoint? We know that the probability of A union A complement is equal to probability of A plus probability of A complement. But this is equal to probability of omega, which is equal to 1. Right? So all these things come from previous things that we have proved. This one comes from axiom or fact 2 that we have proved just now. Finite, then we get a sum. Here they are finite and there are only 2 guys, we get a sum. This is from part 2, fact 2. And this is from the fact that omega, this part here is from the fact that omega is equal to A union A complement. And probability of omega equals to 1 comes from fact, or comes from axiom 1. Right? So stringing all these together, we get that probability of A is equal to 1 minus probability of A complement. Okay, and the other way around, it's fine. Okay? Did I follow? I don't know. Maybe you are right. Yeah. Maybe you're right. Yeah. Then maybe it's easier. But I follow the book, I think. Did I follow the book here? I don't know. Okay. So fact, this is even easier. Fact 4. All right. We have probability. The claim is that probability of A is less than or equal to the probability of B if we have ABs that are events and A is contained in B. A is a subset of B. Again, I use this subset notation. I could have used this instead. These two mean the same thing to me. Okay, so Now we can write the following. B is equal to A, disjoint union, B take away A. Oh, this is a matter of set things. So this is, set should be nice and connected. So this is B, and this is A. So the fact here is that A is this part here, is the B here is the fact is A disjoint union this part. This part here is a disjoint union. B but not A. Beautiful picture, right? Right, so this is a disjoint union. So we make use of fact something, right? So probability of B is equal to the probability of A plus probability of B take away A. Okay, this comes from one of the facts here for finite union. This fact here, finite union for disjoint sets, and these two are disjoint. And now we know that, now we know what? We know that this is non-negative. So we can control this by probability of A, and we are done. Okay, so we can drop the non-negative part. Okay, so fact 5, probability of B is less than or equal to 1. Okay. Right. So probability of B is less than or equal to 1. Oh, this is not so difficult. In the previous, okay, so for it, let this be A to be more consistent for all A event. Okay, so there's a fact we have to prove. Okay, so for the previous, from fact 4, set B to be equal to omega. Then omega is certainly in E, and A is certainly subset of B equals to omega. Right? And probability of B is equal to probability of omega, which by the first axiom of probability is equal to 1, as desired. Right? So we have probability of A less than or equal to a probability of B, which is equal to 1. Okay? Make sense? Halfway there. Let's soldier on. Any questions? Any alternative brilliant solution?
Not a solution, but this fact actually guarantees the convergence of the infinite.
Which fact?
This fact.
Yes. Because this one finite.
Yeah.
Because omega finite, yes.
So no, because of this, your infinite limit for axiom has to converge because it's not bounded.
Yeah. That's what I was trying to say. Because this one is 1. Yeah. Actually, this student here, right? This student, or not Vivek, Yenger. Now I noticed that there is some small issue with Yenger's argument. Okay, so I said this, right? I said this issue here. Suppose I don't constrain my probability operator to be upper bounded by 1. Okay, at the very beginning. Then this argument by Yenger does not go through. Yenger here is using the fact that probability of A is less than or equal to 1. No one said that probability of A here, probability of A should be finite. If I remove this, okay? And you cannot take away, you cannot subtract an infinite number from an infinite number. So to make this super rigorous, we need to have that probability of, we need to have fact 5. So now I think about the fact that fact 5, I prove fact 5. With fact 5, this one is okay, Yenger's argument. Because subtraction, you cannot subtract an infinite thing from an infinite thing. That's not allowed. Okay? But now everything is nice and bounded. So if I did not specify that probabilities are bounded as as I had here, then that argument is not quite watertight. Okay, right. So thank you very much for all the conversations there. All right, so factor 6, I guess. So sum of n probability of an is less than or equal to 1 for any sequence of disjoint events AI. Okay, AI, AN mean the same thing, okay? Proof. And this is not so obvious actually, right? Because the probabilities here, they are non-negative. They could possibly be positive. Could possibly be positive. So you could accumulating more and more. But then it's still bounded by 1, right? So let A in fact 5 above. Okay, fact 5 above be A equals to union AN. Then use fact 2. Okay, so fact 2 says that the probability, fact 2 says that probability of a disjoint union is equal to the sum over AN. And this itself, from fact 5, is an event. And furthermore, this is controlled by 1. So this must be true. Okay. So we have by this notation, I mean by this notation, I mean this whole thing is a disjoint union. Right? Here, we are using fact 2. Fact 2 here. And here we are using fact 5 here. Right? Because fact 5 says that for probability of anything is less than or equal to 1. And here, fact 2 says that probability of a disjoint union is equal to the infinite sum, is equal to some sum, infinite sum of the probability of the constituent events. Okay? Right, so this is not so obvious. The next one requires a lot of work. All right? Probability of union AN, n equals to 1, equals to the limit m going to infinity of the probability union finite AN, n equals to 1. This actually has a name. It's called continuity of measure. This has a name. It's so important that there's a name. Okay? Okay, this is holds true for any sequence of not necessarily disjoint events AI. Okay? Oh, this is not so obvious. Not necessarily disjoint events AI. So all these AIs belong to E. Okay. So we had been dealing with disjoint things previously. And for disjoint events, the probability of the union is equal to the sum. But now this is not so simple because this says that what we are dealing with are not necessarily disjoint events. Not necessarily disjoint. So what can we do? In mathematics, when we don't know how to do something, we look at the previous facts we have proved. That is a general rule of life. Okay, so this is probably the most involved proof of today, probably. I think most involved proof, which says the following. Okay, so we have not necessarily disjoint events. Let me draw a picture first before we prove anything. The idea is the following. I cannot draw an infinite number of things. I cannot draw an infinite number of events. I can only draw 3. So what are we going to do? Right? We're going to, oh, wrong color. We're going to create new disjoint events. We're going to call this B1. And then we are going to call this, this part here, A2, but not A1. We are going to call this B2. And this part here, A3, but not the previous two, we are going to call B3. Beautiful picture, right? So the idea here is that we want to create new events that are disjoint. Look at the B events. The B events are really disjoint. Okay? The proof goes as follows. Create or come up with BI events that are disjoint. And have the property that union AN is equal to union BN. How do we do this? We follow the recipe of my beautiful picture. You let B1 equal to A1. You let B2 be equal to A2 diff A1. And generally, you will let Bn be equal to An, take away union up to n minus 1, Aj, j equals to 1. So this formula here implements this picture here. Okay, these formulas here implement this picture here. And homework, show this property. Okay, now with this, we can actually change this to disjoint union. Because the B's are disjoint, I can use this notation. So hence, probability of union infinite AN, n running from 1, is equal to the probability of disjoint union Bn, n running from 1 to infinity. Aha, what can I do now? Now I have this disjoint union, right? But by one of the previous axioms, this is an infinite sum. Probability Bn. Right, I'm allowed to do this now. I was not allowed to do this just now. But what is the meaning of this? This is limit as m goes off to infinity, m upstairs, n equals to 1 downstairs, probability Bn here. I'm allowed to do this. This is all equality. Right? But now, let's now extract this part here. Let's extract this part here. Look at just this part. And look at the fact how we constructed Bn. How did we construct Bn? We constructed Bn here. So from this here, can you see that Bn is a subset of An? So Bn, look at B3. B3 is clearly a subset of A3. We are taking away from the A's in order, we are taking some things away from the A3 to create B3. We are taking away some things from A2 to create B2. So we have that this property, right? We have this property, right? So what happens here is that, let's consider this, but this is nothing but probability union, or maybe we don't need this. Let me just follow through. These Bn's themselves are disjoint, so we are left with this disjoint union. Okay, but this disjoint union is exactly equal to the union of A's up to n, up to m, because everything is preserved in the finite case, just like in this picture. Everything is preserved in the finite case. So the union of the Bn's up to m is the same as the unions of the An's up to m. Okay, so what have we got by stringing everything together? So by combining equation 1 with equation 2, 1 union 2, this yields that probability of union up to an, n equals to 1 is equal to the limit as m goes off to infinity, this part here. Just put this here to show you I'm not cheating. And that completes the proof. So we had to go through the route of creating this disjoint union first to the B's, and then move back to the A's by considering the fact that not only this is true, but also the following is true. Union up to m of the ANs is equal to union up to m, this is a disjoint union, of the BNs. Okay, we also have this property in addition to the infinite version. All right, so these properties need to be proved, and I will not do it. Okay, so we have the infinite version and we have the finite version. The finite version is easy to see from the picture. The infinite version needs a small little proof. Okay, but this is the whole proof. I'm stringing just 1 and 2 together. Okay, so now we have this. Let's conclude the last fact. So I have an event, not necessary. By this, I just say that this is a subset of B. So each one of them is an event, not necessarily disjoint. Again, as in the previous part. Okay. Then we have that the probability of their union, n equals to 1 to infinity, is less than or equal to sum up to infinity, n equals to 1 of probability of an. Okay. So how do we show this? We have already shown it actually. Okay, so the left-hand side is the probability of union infinite an, n equals to 1. But this, by the previous fact, sorry. The previous fact is fact number 7, right? Look at this previous fact here, number 7, continuity of measure. So this is 8. Okay, by the continuity of measure, this is limit n go to infinity of this, of probability union m a n, n running from 1. Okay, but this one is less than or equal to limit m running from n to m running to infinity of sum running to m here, probability of an. Okay, n equals to 1, and this is defined as sum up to infinity of probability of an equals to 1. By stringing together the previous results. So this has a name. This has a name. This is called the union of events bound. Or by short, union bound. So the union bound is usually stated like this. This is also called the union bound, this part here. That this probability of a finite union is less than the sum, the finite sum of the probabilities. This is usually called the union bound. But the union bound also applies to the infinite case as we have shown here. That's the point of all this work. Okay, so now as promised, we will take a 10-minute break. And then we will resume at 7:38 here. Okay. Those people who have not checked in, please do so. Well, I use the restroom. 7:38, we will resume, okay? Yeah.
Just ask,
Yeah.
I think for this one, for this part,
Mm.
you jump step in the proof.
Yeah, I jump here.
Until, right?
Yep.
You
We
have
need to
switch
prove one
to
more.
VM.
We can. You have to show actually the following. And then use induction for the M
Yeah.
pace. But to show this is not so difficult. Probability A1 disjoint union A2 diff A1. Then this disjoint probability A1 plus probability A2 diff A1 less than probability A1 plus probability A2. Here we jump step.
Yep.
And this is a justification. So M case induction.
Actually,
Yeah.
this segues to a question I have, right?
Yeah.
For our presentation proof, we need to sets, right? Is the power set legitimate? So for finite sets, right, you can take the sample space to be the power set.
Yeah.
But what about for countably infinite?
You can still take the power set to be the signal algebra.
Should we? Okay.
Yes.
So it only starts going wrong when
Countable.
your
Uncountable. Uncountable. Yeah.
Okay.
Has everyone done this? These people have not taken temperature. Xia Hanwen, Zheng Xingjian, Ma Zhentian, and Muhammad Youssef Azmi. Yes. Anyway, fix it. You what?
I couldn't find a database. So I have created my database
Okay.
because it seems like I really love to do it.
Okay, I don't know. Usually this is instant, if we instant refresh. No, these 4 people still haven't.
How do you look at the temperature part?
Can you ask your friend? I'm not a student. I don't know.
I just talking to my better friends, they never ask for it.
You
And declare the app. Yeah. Before you send it.
yeah, you have to declare on the NUS app. So do I actually. Okay. Is everyone back? Okay, now we have to remove our mask and take a photo. Right? I'm following the rules, right? Wait. One person there. Come, hurry up. We need to take a photo. Okay, this side first. We need to remove mask. Waiting for you. Okay, now remove mask. So remove mask. 脱口罩. This side first, huh? Okay, now this side. Okay, I need to upload this. Okay, good, thanks. All right, so let me get back. Let's go back to the Zoom. Okay, so here indeed, I skipped one step here. So here we have this probability of finite union of not necessarily disjoint sets. Who said that this goes to here? All right, who said that the probability of a finite union of a disjoint set becomes the sum of the probability of the sets? No one said so. So this requires a short proof, but we can do this. I'm only going to do it for the 2 sets case. The general case can be done by induction or generalizing this argument. So the probability of the union of the 2 sets is upper bounded by the probability of the A1 and A2. Okay, but this union here can be decomposed into the disjoint union of A and A2 diff A1. And these 2 objects now are disjoint, so we can make use of this. But this set here is a subset of A2, and so we have this upper bound. Okay? So sorry, I skipped one step in the union bound. And in the homework, you are going to strengthen the union bound. The strengthening of the union bound was a quiz question in quiz 1 a few years ago. And only very few people got it. Okay, so now we are going to talk about probability review. Okay. In case anyone joins this, please let me know, okay? All right, probability review. All right, definition. We are going to talk about conditional probabilities and independence is important here. For any 2 events, A, B in E, okay, under a probability model, PR, the conditional probability. Next time we'll talk about conditional expectation, which is very challenging, of A condition on B is defined if probability of B is greater than 0 by probability of A given B is equal to probability of A intersect B, probability of B. So here we are, whenever we write things, we have to be very careful, right? In mathematics, you cannot divide by 0. So the conditional probability of A given an event B whose probability is equal to 0 cannot be defined like this. No one says that it cannot be defined, but it cannot be defined using the following manner. conditional probability of A given events that have 0 probability can very well be refined, but we will not need it for this class, okay? Because we are going to talk about applications of probability. This, for the case where this is equal to 0, it requires us to talk about measure 0 sets, which is beyond the scope of the class, okay? So here we have to be sensitive. Can A intersect B be defined? Can we put A intersect B inside PR? Yes, we can, because it is an event. A intersect B is an event, so we can do this. Okay? Right. So there's a famous rule called Bayes' law or Bayes' rule that says that probability of A given B, probability of B is equal to probability of, you can flip this. Okay. So because both sides are equal to the probability of the intersection. Okay. So this is Bayes' rule. We are always going to use it. Now we can talk about being independence. Two events A and B are independent if probability of A intersect B is equal to probability of A, probability of B. Now, why do I choose this definition instead of this other obvious definition? You can also define independence using this definition. So I can define very well independence using this definition. Why don't I want to do it? Because it will restrict the sets that I can deal with. Because this object can only be defined from what we have learned for B's whose probability are positive. So I've restricted the sets, the pairs of sets that I can talk about being independent. Whereas if I use this definition, any events are okay to be classified as independent or not independent. Okay. So, but as a corollary, all right, if, as a remark or corollary, probability of B is bigger than 0, this is equivalent to probability of A given B equals to probability of A. And hopefully in an undergrad class, you have seen these things before. Okay, all this can be extended to the case of conditional independence, all right? So events, is understood that all these are events already. A and B are conditionally independent of each other given event C, or A, B, C are all events, okay? Otherwise, I'm not going to write it down. We are only going to deal with subsets that are events from now on. Equals the probability of A given C, probability of B given C. So that is the meaning of conditional independence. Okay, so we are going to make use of conditional independence a lot when we talk about Markov chains, but maybe not so soon. Markov chains is after the term break. But now I want you to focus on mutual independence. Okay, mutual independence. The events, we are going to talk about n events. A1, A2, dot, 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 AN, we are n events, n is at least 2, are mutually independent. I wrote independent in my notes, but it's not good enough. Mutually independent. If you would think, all right, you would think, okay, if I do intersection of I running from 1 to n is equal to the product up to n of the probability of AI. You would think that I'm going to write this definition, but I'm going to be very evil and cut this out because it's not true. We need the following. If for all subsets S, subset 1 up to n with size S at least 2, all right? So all non-trivial pairs triples, quadruples, quintuples, and so on, probability intersect I in S is equal to product I in S probability AI. So if I have three subsets, A1, A2, A3, I say that they are mutually independent if I look at all pairs and I look at all triples. There's only one triple in a family of size 3. I look at all 3 pairs and I look at the triple, they satisfy this relation. I need to check the pairs as well to be able to assert mutual independence. So remark, this includes the entire collection, i.e. S is equal to 1 to n. But the statement that I incorrectly wrote down, how come cannot paste? I got to write it again. Probability intersect I equals to 1 to n AI equals to product I running from 1 to n probability AI does not imply statistical independence. Does not imply statistical, I should be consistent, mutual independence among the AIs. Among AIs. Okay? Yeah, so we have to actually check all subsets for independence. So you might wonder whether there's any interesting example for which something like this fails. Okay? That if I only check the full set, basically if I only check this statement here, there are some pairs that are not independent. So I constructed this simple table here. So our sample space is sample point in omega are as such 1, 2, 3, 4, 5, 6, 7, 8, A1, A2, A3. I'll tell you what this means later on. This is a bit confusing, the way I've indexed this. 1, 1. This is properly designed so as to make this example work. Okay, so all these sample points have equal probability 1, 8. Okay, so what this means is that, what this line means is that probability of A1, A2, probability of A1 and A2 and A3 is equal to 1, 8. Okay, this is also 1, 8 here. 1, 8 here, all the way down. Okay, so this means that, What's the sample point? Oh, typo. This won't work. Yeah, this one won't work. This one, thanks. Okay, so if A1 is true, A1, A2, A1, A2, A3 true, probability 1, 8. A1, A2 true, A3 is false, probability 1, 8, etc., etc. Okay, so probability, let's calculate a few numbers. A1, A2, A3, I already said is 1, 8. Look at the first row. Okay, and probability AI. Okay, you see that you look at these columns here. There are 4 ones here, right? 4 ones out of 8 numbers altogether, 8 possibilities altogether. So no matter what I is, for I running from 1 to 3, this is 1, 8, right? Oh, sorry, 1, 2, 1 over 2, right? So it is clear that the probability of A1 intersect A2 intersect A3 is equal to the product up to 3 of probability of AI. So the triple wise relation holds. But we're going to show some funny things now. Okay, so the triple wise relation clearly holds because here you see that there are 4 ones, right? 1, 1, 1, 1, 4 ones here. Right, 4 ones. So the probability of AI is each one of it is half. Okay, yes here. So half times half is 1/8 as desired. So this is all 1/8. Right, so triple wise we are okay. But in this particular experiment, unfortunately this screen is not big enough. So, however, let's look at probability of A2 and A3. Okay, A2 and A3 is on only this row. What color you like? This color. A2 and A3 are on at the same time. Only this row. Oh, I'm sorry, I don't mean to do this. I want the highlighter. Only this row, which means we only collect 1/8 mass. All right, so this part here is 1/8. Right, but this is not the same as probability of A2 multiplied by probability of A3, which is a quarter. So we violate the pairwise independence of A2, A3. Okay, so in fact, events A2 and A3 are not independent. Not independent means dependent. As another example, very strange example, probability A1 complement intersect A2 complement intersect A3 complement. So what are we looking for? If I want to calculate this, I'm looking for any row that has all zeros. Which row is all zero? You show me. None. So this is equal to 0. But this is not the same as 1 minus probability of A1, 1 minus probability of A2, 1 minus probability of A3, which is equal to 1/8, because each one of the products is half. So once if we did have independence, if we did have mutual independence throughout, then the fact that, sorry, how do I get rid of this? Okay, the fact that we have this is true would also mean that this is true. It is easy to show, and it's an exercise. But because we don't have independence, mutual independence, we not only violate a pairwise independence relation in the purple part, but we also violate the complement condition here. Okay, but you can check that the others are fine. The other pairwise are fine. A1, but according to my example. So these are pairwise independent in this sense. A1, A3. So there are some subtleties, okay? These are okay, these are pairwise independent, but there's one pairwise independence that is violated, the purple one, and strangely also complements the A1 complement, A2 complement, A3 complement is not triple-wise independent, okay? So this means, for example, that A1 independent A2. This means A1 independent A3. Okay. Okay. So we have to be careful when we talk about pairwise or mutual independence. Mutual means everything. Okay. Right. So we talk about events. First we talk about events. We talk about probability. We talk about conditional probability of A conditional B. We talk about base rule. Okay, we talk about independence. We talk about conditional independence, and we talk about mutual independence, which is rather subtle. Okay, this is one thing that is rather subtle, and you can play with this later on, okay, in the homework. Now I want to talk about random variables. As I said, if you have not seen probability before, this is too fast. And I don't apologize for being too fast because I told you that it's going to be too fast. But this is not a class on probability, so I have to go through this very quickly. Okay, so I want now to talk about random variables, which is what this course is really about. This course is really about many random variables. A stochastic process is a family of random variables. It could be a finite family, but that is uninteresting. We are going to talk about infinite family of random variables. Random variables that are indexed by time. Now, time can proceed in discrete time. Time 1, time 2, time 3. We're going to see a stochastic process of this later on. But more interestingly, the stochastic processes that we will study are indexed by continuous time. So at time pi, something happens. At time e, the natural number, something happens, right? So when we talk about Poisson processes, we will talk about continuous time stochastic processes. Those are more interesting than discrete time process, right? Because discrete time, nothing much to talk about, but we will still see that some continuous time processes are actually limits in certain senses of discrete time stochastic processes. But before we can, there's one person here. Before we can talk about, what do you want to say? Before we can talk about stochastic processes, I need to remind you about what are random variables. Right? Random variable. Because before we can fly, we need to know how to walk. All right? Definition. The random variable is RV, okay? A random variable, X, is a function. This is very strange. A random variable is a function. It is neither random, nor does it have any variables related to it. So random variable is actually a very bad name for random variable. There's nothing random about it. I don't even know what's the meaning of random because I only know what is a function, a set. These are primitives in mathematics, right? So I know what is a function. A function that maps, I'm going to draw a picture later on, from the sample space omega to the real line, i.e. X brings you from omega to the real line such that the pre-image omega in omega such that X omega is less than equal to X is an event. I already said this, I'm saying this 2 times. Is an event for all X in R. Now, this is very strange, the way we define this. Actually, not we are not so smart. At least I'm not so smart. All right, this is a Komograph, right? So a random variable is a function that is basically a function that brings you from, a function is something that brings you from one set to another set. Okay, what set does it bring you from? Brings you from sample space to the real line. So here is a picture. So here is your sample space. This is the real line. Any random variable takes you from sample space to a certain point on the real line. That is the action of X. And this is little omega in omega. It brings you to X omega, which is a number. Okay. Now, not all such functions that bring you from omega to R are legitimate random variables. Not all. Cannot. Which are the legitimate random variables? Legitimate functions that are random variables. They have to satisfy this condition. If I look at the elements of omega in omega such that X omega is less than or equal to X, look at this set. This is a subset of omega because of this relation here. It's a subset of omega. This is a subset of omega. But this subset of omega, there are legitimate subsets which are called events, and there are illegitimate subsets that we don't like. Now, we have to make sure that this set here, okay, we have to ensure that this set here is an event for every X that we query. That's the meaning of random variable. And the X that we query is a real number, okay? So this is extremely, to you, if you see this for the first time, right? If I see this for the first time, I'll be confused. So if you're confused now, good, you are like me. So example, you need an example, okay? Omega has 3 objects, A, B, and C. A 3-sided coin, if you wish. And our function looks like this. XA is equal to half, XB is equal to 1, and xc is equal to 3 over 2. Let's say this is a legitimate random variable. It's a function that brings us from the sample space to elements that are real numbers. This is what it brings us from, say, this is A. So our random variable brings us to the number half. And this is B. It brings us from here to number 1. And C, this is an ugly color. It brings us to 3 over 2. Okay? And generally omega to x omega. All right? So now let's look at these so-called pre-images. Let x be equal to 1.1. Okay? 1.1 is certainly a real number. Then let's look at the set. Look at the set. Okay? Omega in omega such that x omega is less than or equal to x is equal to 1.1. Now, what are the elements that are less than 1.1? So now I'm going to put 1.1 here. I'm going to put a bar here, which is 1.1. You cannot see this number. 1.1 here. So which are the elements of my sample space that are such that x of those elements is less than 1.1? Which one? A and B, exactly. Okay, and everyone will ask the question: is A and B an event? Now, if our sigma algebra contains A and B, then A and B is an event. That means X is possibly a legitimate random variable. We need to sweep through all possible X to ask this question. But if A and B is an event, and notice that whether or not a set is an event, all right, depends on what is the sigma algebra that you start off with. So whether or not X is a random variable depends on what is the sigma algebra that we assign to omega. All right, so if I fix a certain sigma algebra already, that is my E. I fixed my E already. Then I can ask the question whether X is a random variable or not. Okay, so if indeed AB is an event, then we have done a simple check that, okay, at X equal to 1.1, we are not violating the situation yet. All right, now we need to sweep through all possible X. Let me do one more X. Okay, let X equals to 0.4. This is certainly a R, it's a real number. Then let's look at omega in omega such that X omega is less than X equals to 0.4. Now, it is not difficult to check that this is equal to empty set. Now, empty set is an event. We proved that. This is an event. So actually at the point 0.4, we have checked that X omega, X actually, the perceived random variable, still satisfies some conditions that it's a random variable. But we need to actually sweep through all possible values of X to check whether the resultant set, this sort of pre-image set, all right, this sort of set actually belongs to the E or not. We need to run through all possible values of X. But oftentimes we don't need to do this, okay? But this is the formal definition of random variable. It depends on what your sigma algebra, how your sigma algebra was defined. Right, your sigma algebra was defined based on the sample space. For a given sample space, there are many different sigma algebras. All right, so for example, this is for a sample space ABC. You could have your sigma algebra consists of this and this. This is a legitimate sigma algebra. You check all the conditions of sigma algebra. This is a legitimate sigma algebra. Completely legitimate. If this is the sigma algebra, if E is the chosen sigma algebra associated to omega, then X, as defined in the previous example, is not a random variable. Why? Because AB, does not belong to E. Because you see, does E belong to here? Does AB belong to here? No, it doesn't. Right? So if I create this sigma algebra, this is called a trivial sigma algebra, then X as defined above here is not a legitimate random variable. All right? It's not, the sigma algebra is not rich enough. However, if omega is as usual ABC, then and E is equal to the power set of omega. So this means empty set, all the singletons, all the pairwise, and there's only one triplet. This is equal to the full set. So this is a sigma algebra. If this is a sigma algebra, then X above is a legitimate random variable. You sweep through all the X's, you can find that the resultant pre-image sets certainly belong to one of these candidates. This is the meaning of random variable, whether you like it or not. This is how people define random variables. Okay, so, okay. Now, once we have this notion, it allows us to define, usually the mapping of X from omega to R is not so important. The next concept is more important. All right, usually the mapping, no one really cares because we want to understand the distribution. Okay, the cumulative for any random variable. Okay, sigma algebra is fixed already, so we can talk about random variables. The cumulative distribution function or CDF of X, a random variable, is fx of X. So this is uppercase, big X. This is small case, lowercase. My uppercase and my lowercase look the same. Sorry. Okay, live with it. Probability omega in omega, X omega less than or equal to X. Now, at this point in time, right, you have to jump up and ask the question, can I write this down? Yes, I can, because X of, I forget to say this, of a random variable X is. Because I said that X is a random variable. So this means that this set here is actually an event, which means that I can plug it into the probability operator. This allows me to talk about probability of this purple thing. Otherwise, I cannot even talk about the probability of this purple thing. Right? So now that I can talk about the probability of the purple thing, which is an event, I can define this function. This function, fxx, here x is an element of the real line. I can define this function. Because why? The purple thing is an event. And the event, you can put it into the probability operator. Cool? Usually people don't write things like this. It's too cumbersome. People just write probability x less than or equal to x. With the understanding that x less than or equal to x is really the purple thing. Okay, you often see in undergraduate probability x equals to x, x less than or equal to x, x greater than x, right? But really it means this, the purple thing. We are referring to the probability of some element, some event in the sample space itself. So when we talk about x less than or equal to x, we are referring to this space here. But really we are measuring some elements here. We are going back. That's what we are doing when we talk about probability. Okay? This is the formal way of doing things. And already I'm being a bit informal. Okay, so now that we have this definition, we can state a few facts. All right, number one, the function x maps to fxx is non-decreasing. Note that when I talk, I'm always very formal. When I say non-decreasing, I really mean non-decreasing. Okay, I don't mean increasing. All right, So why? All these can be proved. I'm not going to prove them. Why? What is the meaning of non-decreasing? If I take x and y is at least as large as x, then fx of x is at least, is at most, fx of y. Talk too much. So that means, i.e., if for every x, y such that x is less than y, we have fx, x is less than fx, y. Okay, that's the meaning of non-decreasing. Okay, so that follows from the fact that, all right, that follows from the fact that omega in omega, x, omega less than x is exactly, getting tired already, subset here, and you replace this by y. And then we make use of the fact that the probability of the left side is not larger than the probability of the right side. This is one of the probability axioms or facts that we proved. Is this clear? Yeah. So this is the first fact. I'm not going to prove the rest, okay? I'll state this. So limit as x goes to minus infinity of fx of x is equal to 0. Limit as x goes to plus infinity of fx of x is equal to 1. You prove this. And fx dot, this means the function is right continuous. Okay, this requires a little bit of thinking, but right continuous means the following. Limit epsilon go to 0 plus of fx of x plus epsilon equals to fxx for every x in R. Not necessarily right continuous. Okay, it's not necessarily left continuous, it's definitely right continuous. Okay, right continuous follows from something that we have proved. Exercise for the good student. Okay, exercise. I don't know whether I assign this as an exercise or not, but this can be proved from everything that we have talked about previously. It can be proved from particularly continuity of measure. All right, hint, exercise. Because I don't want to do it now. Right, so special case. Okay, if x has a finite or countable number of possible values, so the random variable can only take on finite or countable number of values. So just now I had the ABC example, right? So x can only take on 1, 2, 3 values. ABC, the sample space only has 3 values, ABC. All right, x can only take a finite or countable number of values, like half. Sorry, x can only take on half, 1, 3/2. Okay, so that's this situation. X has a finite or countable number of possible values. Say little x1, x2, x3, dot, dot, dot. The probability PR, x equals to xi, of each sample xi is called the probability mass function. You may have heard this before. Don't know what this is in some other countries, but where I was educated, it's called probability mass function, evaluated at xi. And we usually abbreviate this as P of xi. Sometimes we call Px of xi. This is probability of x equals to xi. So I runs from 1, 2, all the way. Now, people, by this time you know me already. You know I don't like to write anything I like. I don't like to anyhow write things. What's wrong with the thing in the red box? What's wrong with the thing in the red box? So the red box stuff is the following, written out in its full glory. Omega in omega, x omega equals to xi. That is what is the red box. You know, this is equal to probability of x equals to xi. Well, what's wrong with this? You have to be sensitive to this. Who says that the thing here, who says that this set here is an event? No one said so, because we only know that if this inequality is less than equal, this is an event. For every little x. If capital X is a random variable, then if I have this less than equal, it is an event, less than equal. But if equal, how? Is it an event? This requires a proof, right? Do people at least see the subtlety that we have not proved something? If this is equal here, or here, sorry, you cannot see here, right? If this is equal here, no one says that the thing in purple is an event. It belongs to E. This need not belong to E at first sight, but it does belong to E at second sight after you prove things. So I'm going to upload a document today after this lecture ends to show you that this belongs to E. I have not uploaded it. But do you see that there's something to prove here? There's something strange here. Because if capital X is a random variable, then then I have the less than equal part. This is indeed okay. Equal may not be okay. Less than may not be okay. Greater than equal may not be okay. No one says that it's okay. But what we will show is that no matter what you have, as long as X is a random variable, you're allowed to have this less than equal, of course, greater than equal, of course, and equal. All these are events. Do you believe me? Do you know that there's something to prove? You need to be sensitive to that there's something to prove here. Okay? Cool? All right. So this need not belong to E at first sight. But after a few lines of proof, it is indeed an event. And so we are allowed to write probability X equals to Xi. Okay, that's my remark. You see, we cannot anyhow do things. We have to do things systematically and slowly. Okay, so in the case of discrete random variables, or this X taking on a finite or countable number of values, then our cumulative distribution function looks like this. Okay, so here is our x1, here is x2, here is x3, and we go this way. Oh, it is this empty. Here is something here. This is gone here. This is nothing here. This is something here. Nothing, something here. Suppose we only have 3 values. Then we go up to the level 1. This is level 0. And what is this here? This here is P of x1. This here is P of x2. And this is P of x3. Okay? So that's the picture for discrete random variables, the cumulative distribution function. Cumulative distribution function. And you can see that this, what I mean here when I circle this is that fx at x3 is equal to 1. That's what I mean when I circle. And fx x3 minus, that means slightly to the left, is 1 minus p of x3. That's what I mean by the circle and no circle. Okay? Right. Okay, but this class requires you to know discrete and continuous random variables. This is called discrete random variable. So I have to talk about continuous random variables as well. Okay. So if this fx, this capital Fx, the cumulative distribution function, right, is the mother of everything. All right. we can define fx of x for any random variable. But then you may have heard of the probability density function. All right. If it has a derivative at x, better don't do this. If fx has a derivative at x, that's better. The derivative, too long-winded. It is called the probability density function, or PDF, evaluated at x. Okay, and it's written as fx of x. Again, this is uppercase and this is lowercase. All right. So in other words, little fx of x is equal to fx prime of x, or we can write this like this. Fx of x, here x is in R. All our random variables are real valued random variables. There are other things that are happening out there that we don't have to worry about. Okay, good. So this fx of x has a certain property. So in particular, there's a certain interpretation, fx of x multiplied by delta, delta small number, small positive number, equals to probability, roughly equals to the probability of x less than equal to x less than equal to x plus delta. But this is the meaning. The meaning here is x to x plus delta of fx of x dx is So therefore delta small, this is the interpretation. Okay, why is it the interpretation? Because this is equal to capital Fx of x plus delta minus capital Fx of x. All right. And this is can be approximated by this, by some sort of mean value theorem. Okay, but we don't need to worry about too much. We don't need to worry too much about this, but we have to have this picture in mind. So the probability density function looks like this, for example. Okay, this is fx of x. It integrates to 1, just to remind you. And now let's consider a certain x here. And here is x plus delta. So this strip here is of width delta. So we want to understand the area here. Okay, what is the area? All right, the area here is basically, how do you calculate it? You can calculate it by integrating fx of x dx from x to x plus delta. Actually, to be better, right? To be more careful, let's put t here. All right. So this is approximately, if everything is nice, continuous or something. All right. This is delta multiplied by fx at x. All right. So there are some conditions for which this is this sort of approximation holds, but we don't need to go too deep into this. So what we need is the following definition. A random variable x is said to be a continuous random variable. Continuous if for every x in R, there exists this function fxx, or this value fxx, all right, which means, okay, in other words, the cumulative distribution function is differentiable at every x in R. Okay, so in this case here, fx of x, all right, can be written as the integral of the PDF up to x. Okay, I think you have seen all these things before in an undergraduate probability class, so I will not belabor the point. Okay, so what this is doing here, this equation is doing here is the following. So let me just copy my picture. Okay, like this. Same picture. What this picture here is doing is the following. Okay, so I have a certain x here. Okay, and I want to evaluate what is the probability. So this, what is the meaning of this? This is nothing but the probability that x is less than or equal to x. So what I will do is I will integrate all the way from the left-hand side up to x. Here. Okay, make sense? Yeah. So that's implementing this formula. I think most people have seen this before. Okay, so I will not belabor the point. Okay, so very quickly, I want to talk about two more things before we call it a day, because I am tired and you are tired. All right, so you should make yourself more tired by doing my homework problems after this. Okay, but before we call it a day, I want to talk about multiple random variables, and I want to talk about our first stochastic process. So, as I mentioned, stochastic process is a study of infinitely many random variables. Before we fly, what must we do? We must know how to walk. I talked about one random variable. Now I'm going to talk about finitely many random variables. Okay, so we have x1 up to xn. These are our finitely many random variables. Very soon we are going to talk about infinitely many RVs. We can talk about their joint CDF, which can be written as fx1 xn x1 up to xn. This is nothing but the probability that x1 is less than x1 and xn is less than xn. Okay, sorry, run out of space. So that's a generalization of the standard situation where we only have one random variable. So more precisely, this is probability of omega inside the sample space for which x1 of omega is less than little x1 and xn of omega is less than xn. Okay, so that's the long form of it. Okay, so given, let's ask ourselves a question. Given a joint CDF, how do we get the CDF or cumulative distribution function of a single random variable? This is usually called marginalization. This is called marginal CDF. Suppose I'm only interested in the ith one. Okay, so I fix an I from 1 to n. Okay, and I'm interested in fx I xi. So what I do is nothing but I set the CDF of the n random variables. I set everything to be infinity except the ith one. Why? Why is that so? Now, if I set everything to be infinity, so say the ith one is here, the ith random variable is here, then I set this to be infinity, I set this to be infinity, then these two are not active anymore. So I'm only keeping the constraint that xi is less than xi. Everything else is no longer active. So they are killed. You see, this is no longer active, this is no longer active, only the ith one is. If I set everything to be infinity. Does that make sense? Okay. All right, so that's the way we recover marginal CDF from a joint CDF. All right, so in the same way, we can talk about the joint. We can talk about the joint PMF. All right, that is Px1 up to xn, x1 up to xn. That is nothing but the probability that x1 is equal to x1, xn is equal to xn. I should try to be consistent here. Okay, so that's the joint PMF. There's nothing much to say. Okay, independence of two random variables. So we say that two random variables are independent. You know, why do I have to belabor this point? Just now I talked about independence, but I talked about independence of events just now. So now I need to talk about independence of random variables. You can talk, in fact, you can talk about independence of sigma algebras also. That's more fundamental. Okay, but two random variables are independent if they are joint CDF factors. this is f y for all x, y in R. So the joint CDF factors. Okay, and if x and y are discrete, okay, then this is equivalent to the PMFs, or the probability mass functions, xi, yj, equal to px, xi, py, yj, for all xi and yj. So xi, yj are the sample points of the x and y's respectively. Okay, so this is all hopefully very natural. All right, very natural to everybody. Are there any outstanding questions? So I think this is quite natural. Independence of random variables is basically that the cumulative distribution functions factor. I think this is something that you have seen before in the undergraduate class, so I will not stop too much to ask whether you have questions. I'm just reminding you, okay? But now we come to something that you probably have more excitement about and motivation for studying this class. We come to our first stochastic process. Now it's time to talk about our first stochastic process. It's called the Bernoulli process. Example of a stochastic process. This process is called the Bernoulli process, and it's very fundamental. Okay. Definition. What do we mean by a stochastic process? A stochastic process is an infinite collection of random variables defined on a common sample space omega. So we have a single common random omega sample space. You can define many different types of random variables on it. And a random variable is nothing but a mapping from the sample space to the real line, as I showed you just now. Right? This is nothing but this. There's one random variable. We fix a sample space. Let's fix a sigma algebra. Fix a certain sigma algebra on it. You can have multiple random, you can define multiple random variables. This is one random variable, you can define another one. So you define many random variables, each one indexed by time. Okay, that constitutes a stochastic process. The sample space must be the same. The random variables don't have to be the same. They don't have to be independent. They don't have to be anything, but they need to be defined on the same sample space. The random variables, sorry, the handwriting getting very, very bad. The random variables are usually indexed by an integer and representing discrete time or a real valued parameter t representing continuous time. Okay. This n and t are interpreted as discrete time or continuous time, but they all represent time. Now, random variables are usually indexed by an integer n or real value parameter t, representing continuous time, discrete time. But these are not the only stochastic processes in the world. You could define a stochastic process on a grid, like here, two-dimensional grid. All right, so you could have a stochastic process X that is indexed by n and m as well. All right, but it is, of course, going to be a difficult thing to study, more difficult. All right, you can define a stochastic process in space as well. But for the purposes of this class, we are only discussing one-dimensional stochastic processes. They are indexed by n or t. Okay. So the simplest thing to talk about is just discrete time, one-dimensional stochastic process. Definition. a Bernoulli process, okay, is a sequence of IID binary. A binary random variable is also called a Bernoulli random variable. Z1, Z2, Z3. These are a sequence of IID Bernoulli random variables. This is your first stochastic process, and they are IID. Now, if they are ID and they are binary, all we have to specify is P, which is the probability that Z1 is equal to 1. Okay? Then because they are ID, that is also the probability that Z2 is equal to 1. We can define Q is equal to 1 minus P, which is probability of Z1 is equal to 0. Okay, so this binary or Bernoulli random variable, the support is 0, 1. You can define Ising random variables. The support can be -1, 1. All right, but they are isomorphic, so who cares? All right, so the interpretation, usually when we talk about these sort of random variables, things like that, we want to tell a story. Without a story, it's very difficult to motivate why we care about these things, right? So the event Zi equals to 1 means that a customer arrived at your store, arrived at your hawker store maybe, arrived at time I. That's the meaning. All right, I'm going to use this interpretation to talk about this stochastic process. And if Zi is equal to 0, then a customer did not arrive and you are sad because there's no customer at time I. This is the interpretation. Okay, so this is a sequence of IID random variables. It's a 0, 1 random variable, but based on the sequence of random variables Zi, okay, we can define another sequence or family of random variables. We can define this sequence as n, which is the cumulative running sum up to n. Nothing is stopping us from doing this. Right? Now then you can ask yourself, are the SNs IID random variables? What's the behavior of the SNs? Are they independent? Is S1 independent of S2? No, clearly not. Because if S1 is very large, you know that S2 is also very large. Okay? So independence means if I know something about you, do I have further information about the other person? Right? If I know something about S1, do I know something about S2? Yeah. If S1 is equal to 1, S2 is at least equal to 1 by this construction. Okay? So here's a picture. Hopefully I can draw this picture beautifully. Okay. Oh, no. It already turned out to be not beautiful. So this is here, discrete time. I start off with 0, 1, 2, 3, 4, 5, 6, 7. And I need times 8 time slots. This is n. Okay, now I'm going to write down my Zi's here. They are 0, 1, 1, 0, 0, 1, 0, 0. So at time 1, there was no customer that walked into my shop. At time 2, 1 customer walked in. Oh, you cannot have 2 customers walking in, sorry. Think of it as the time slots are too small for 2 customers to walk in, okay? So at time 3, 1 customer walked in, and then no more walked in until time 6. So this is my process Zi. Okay, what is my process Xi, Sn? Okay, let's say S. Here I have Si or Sn is better. 0. Sn is the cumulative number of customers I have in my shop. All right, you might think that my shop is very small, but my shop has infinite capacity, say. Okay, I can accommodate 1 million customers. So let's consider this 2 here. 2 customers, no one walked out. 2, 2, 3, 3, 3. Right? So that is a sample path. That's a realization of my Z's which leads to a realization of the S's. Okay, so now we can draw the sample path as well. So this is at this point here, we have no customers. So we have, at this point, we have no customers. So we have S is exactly equal to 0. Then we jump up. And then we have one customer at this point. Until 3, we have one more customer came in. Then we have a constant number of customers here. And then we have 3 customers and so on. Okay, so we can also define another sequence. So this is the S random variable, Sn, right? This is the evolution of my S. We can define yet another sequence of random variables, which is our inter-arrival time, x1, x2, x3. Those are the inter-arrival times. The amount of time you need to wait for one customer to join your shop, to pop into your shop. How long do you have to wait for one customer to pop into your shop? So we started off with the Z random variables. Then we have the S random variables. And then we created another set of random variables, which are the X random variables. So we can then define these Xi's are known as the inter-arrival times. Okay. And they are given by a specific formula. So Xi is nothing but Si minus Si minus 1? Hang on. let me not do this first. Okay, let me write down something else first. So the Xi's are the inter-arrival times. They are the times you have to wait in order to get a new customer into your shop. All right. Consider X1, the first inter-arrival time. Okay. Okay. What is its distribution? We want to try to understand what is the chance that X1 is 2 or 3, etc., etc. So so the question is what is its distribution? This is the short form for distribution. So how can we get X1 equals to 1? X1 equals to 1 means that Z1 must be equal to 1. Do you agree? That means we only waited one time slot for the customer to come in. And P of X1, 1 is equal to P. Because Z1 is equal to 1. And the probability that Z1 is equal to 1 is exactly P. Now we ask ourselves, X1, let's consider X1 equals to 2. What's the chance that we have to wait a time of 2, discrete time, so that what's the chance that we have to wait 2 time slots before a customer walks in? What stars have to align for this to happen? Well, Z1 must be equal to 0 and Z2 must be equal to 1, just exactly like this situation. Then X1 will be equal to 2. You agree, right? We need to fail the first time and we then succeed the second time. Right? And this probability, X1 equals to 2, is we fail the first time and we succeed the second time. Now, one more exercise. X1 equals to 3. If and only if Z1 equals to Z2 equals to 0, but Z3 is equal to 1. In which case, you fail 2 times and you succeed the last time. Understand? This is a geometric random variable. You may have heard of this before. Geometric random variable. So more generally, P of X1, J is P, 1 minus P, J minus 1 for J at least 1. Okay? So look at this. We started off with the Z stochastic process. Then we did some manipulation to get the S stochastic process. Then we talk about the inter-arrival times. The first inter-arrival time has this distribution. Okay? Claim. Claim means you prove. I don't want to prove. All right? P of xk, all right, is the same as P of x1, the probability mass function of x1 for every k in n. All the inter-arrival times have the same distribution, all geometric. Okay? All geometric. Okay, so this is something that one can prove. Okay, this is claim 1. I come up with my own claim. All the inter-arrival times xk are mutually independent. Oh, this also requires a big proof. Not big proof, but it requires a proof, a justification, just like the first claim. All these exercises. But this is show you that even if we start off with some simple stochastic process like a coin toss process, we can come up with very interesting processes like the X process. Okay? So another question is, what's the distribution of the partial sums, which is Sn, sum Zi up to n. Okay, so each Sn represents the number of arrivals to your shop up to and including time n. Right? So look at this picture here. So if I look at a particular time here, 7, it represents that 3 people have come into my shop. Right? So what events must fall into place for this to happen? Okay, what is the chance that probability of Sn is equal to k? So k people must walk into my shop in this n time slots. So in n minus k time slots, we must make sure that no one walks into my shop, right? So here you have n time slots. Here you have n time slots. And say k is equal to 3. So what we need to happen is that we need to choose 3 time slots for people to walk in, and the rest, no one can walk in. So more generally, this is n choose k, succeed k times, and fail n minus k times. And here k runs from 0 to n. This is called the binomial distribution. Okay, so just from the Bernoulli process, we managed to create geometric distribution. We managed to create the binomial distribution. And you will see that if I let these intervals of the Bernoulli process become super small, I will get what you will learn, the Poisson process. This requires a big proof. Okay? Oftentimes, we want to study this sort of behavior for large n, large k. We're going to study the asymptotics, the behavior of this sort of thing for large n, large k. So we will study this in the context of large deviations shortly. So I finished talking today. I hope you learned something. I know this is a crash course. It's meant to be. It's meant to be a crash course in probability, but you read the book, section 1.1 to 1.4.1, and you do the homework. All right. The optional question is optional, but it's good for you to try. Okay, you can talk to me if you want, but we are calling it a day. Have a great weekend. Thank you. The Zoom people are also logging off. Okay.